All right, guys, in this video, we're going to introduce the idea behind sequences and series, which is going to kind of set the stage for all of Unit 10. So I'm going to go as slow as I need to, slow as possible, just to get that good background on sequences, what it means to be a sequence, and how you can make a series. So some of the stuff you might already know. We won't necessarily reference all this from now on, but this kind of gives us that background. All right, so consider this following list of numbers: 1, 4, 7, 10, 13, 16. How would you suppose this list is generated? So this list is a sequence, and each number is a term in the sequence. So I would reference this first term with an A sub 1. The next term would be A sub 2. Next term, A sub 3, on and on and on. And I can say the nth term would be A sub n. And I've got the squiggly braces to represent, it's a sequence of numbers. And this one, you probably tell, it's just I started a number, and each one I add 3 to the previous term to get to the next one, just adding 3. So the subscript would be called the index. A sequence will often start as index is 1, but sometimes it could start at 0, and sometimes we might even start it like way later in the sequence. But there are 2 ways to define a sequence, as illustrated below. We've got a recursive definition and an explicit definition, and we'll be working mostly with explicit definitions. So a recursive definition, or implicit, each term in the sequence is 3 more than the preceding term. So for the implicit, I need the term before it to represent that next term. So A sub 1 just starts at 1. In order to define A sub 2, the second term, I need the term before it, plus 3. So the third term, I need the term before it, plus 3, so on and so on. And I could write it in general terms like this. The benefit here is pretty easy to see. We just added 3 each time. The drawback is, and if I want to find the 50th term in the sequence, I would need the 49th term. And to get the 49th term, I would need the 48th term, so on and so on. Okay, explicit definition. Each term in the sequence can be represented by an ordered pair. So first term is like 1, second term is 2, third term is 3, and then the actual term. And what I look at this is I think of this almost like a function, right? Where I just plug in x's are going to be just 1, 2, 3, 4, not necessarily all the ones in between. So the slope is the difference, or it's the difference of y's over the differences in x's. So in this case, it's 3. And then the starting, as I would just use this whole idea behind point slope form, right? I've got point y is equal to m, x minus x1 plus y1. Distribute the 3, 3x minus 3 plus 1, y is equal to 3x minus 2. And back in your pre-cal days, or maybe algebra days, you could just count the terms backwards, like y is 7, go back, it's 4. Go back 3, it's 1. Go back 3, it'd be negative 2. So the benefit here is I can use it easier to find terms deep in the sequence, like the 50th term. The drawback, sometimes it's kind of harder to see, and sometimes if it's not well behaved, it's kind of hard to write the equation for it. All right, so just a little backdrop. Okay, use the explicit formula for each sequence. So they're giving us the explicit form to write out the first 4 terms of the sequence. Okay, so let's just get a practice, make sure this is concrete in our brain. So the first term, I get that by plugging in 1 for n. Be 1 over 2 to the first power, so just 1 over 2. The second term would be 1 over 2 squared, which would be 1/4. The third term, plug in 3 for n. This could be 1/8. The next term, plug in 4, 1/16. Okay, those are just the terms in the sequence. I keep going on and on and on, but those are just the first 4. All right, the next one, and maybe just notice some things, like notice each time the terms are being cut in half. No, that's not important right now. Okay, stay focused. Okay, this one, first term. Okay, plug in 1 for n, so this is negative 1 to the first power times 1 over 1 squared plus 1. All right, so in this one, negative 1 to the first power is negative 1, times 1 would be just negative 1 still, over 1 squared plus 1 would be 2. Okay, the second term, the exponent is 2 now, times 2 over 2 squared plus 1. All right, so the first one was negative, and it was negative because of that. Okay, this one's going to be positive because negative 1 to an even exponent is positive 1, and 1 times 2 would be 2, over 4 plus 1 is 5. Okay, the third term in this sequence, now negative 1 to an odd exponent, times n over n squared plus 1. This would be negative 1 times 3, so I'd say negative 3 over 10. Okay, fourth term, running out of room. It's negative 1 to an even exponent times 4 over 4 squared plus 1. 16, that'd be over 17. But it'd be positive 4 because negative 1 to the positive, or no, negative 1 to an even degree, that's my highlighter, gives us a positive. So I want you to think for a second, it's going to be a big idea later on, is why does this alternate from positive to negative, or negative to positive, negative to positive? And it was all from this negative 1 to an odd exponent, negative 1 to an even exponent, negative 1 to an odd. So it alternates back and forth between negative and positive. That's going to be a big thing later. Just start thinking about it. All right, graphically, the two sequences look like this. So in both cases, the y numbers, the terms, are approaching 0. But this one is approaching from positive, negative, positive, negative, positive, negative, but still those numbers are approaching 0. So that's an idea. All right, let's keep going with some more examples. Working with a sequence. Okay, find the next two terms of the sequence, find a recursive definition, and then find an explicit definition. So recursive needs the term before it to find the next term. Explicit is like a little formula. All right, so part 1, the next two terms of the sequence. I got to figure out what's going on. Okay, it's not alternating. It's just kind of going from negative 2 to 5. It went up 7. 5 to 12 went up 7. 12 to 19 went up 7. That's the first, second, third, fourth. So the fifth term, I could say a sub 5 is equal to 26. And then a sub 6, add 7 to that, and it would be 33. Okay, part 2, find a recursive definition. So A1 is defined to be negative 2. So the nth term, okay, let me write this first. The second term would be the term before it, plus 7. So the a to the n plus 1 would be equal to the nth term, like the one before it, plus 7. So if I want to find the seventh term, plug in 6 for n, and I can find it that way. All right, next, Part 3, find the explicit form. So this is linear, which is arithmetic sequences. If it's going up at a constant rate, those are arithmetic sequences. If they're being multiplied by a constant number, it's a geometric sequence. So this one's arithmetic. Means it's linear, so I could say a sub n is equal to the slope, the rate of change is 7, x minus 1 minus 2. So this is 7x minus 7 minus 2 is equal to 7x minus 9, which I could have also gotten by just going back from, in my pattern, do negative 2 minus 7, get negative 9. All right, there we go. There's a recursive definition, or explicit definition. All right, part B, just working with sequences. This sequence is defined to be B of n, so I would say B of, 1, 2, 3, 4, 5, so B of 6. Okay, this pattern, it went up 3, then up 6, so it's not a constant linear, but each time I multiply by 2. Take the term before it and multiply it by 2. That's called a geometric sequence. So the sixth term would be 96. The seventh term, I almost called it A, it'd be B of 7, is equal to 192. Okay, a recursive definition uses the term before it. So I'd say A1 is equal to 3. So the next term, A to the n plus 1, would be equal to 2 times the term before it. So 2 times A sub n. Okay, kind of helpful, but not really, because I need to know the terms before it. The explicit was really nice. So let's kind of think. I'm going to erase, I need some room to kind of think here. We want to write like an equation where I can plug in an n number and it would pop out that term of that nth term. So I'm going to say A sub 1 is equal to 3. A sub 2 is equal to 3 times 2. A sub 3 is equal to A sub 2 times 2 again, right? Which is equal to 3 times 2 times 2. A sub 4, I'm going to say this is 3 times 2 times 2 times 2. A sub 5 would be equal to 3 times 2 times 2 times 2 times another 2. So this would be equal to 3 times 2 squared. This would be 3 times 2 cubed. This would be equal to 3 times 2 to the 4th, on and on and on. So in order to find the third term, the exponent was 2. In order to find the fourth term, the exponent was 3. In order to find the fifth term, the exponent was 4. So explicit form would be A sub n is equal to 3, it's always 3, times 2 to the n minus 1. Now I can plug in any function or any value. If I want to find the 50th term, plug in 50 for that n, and that would tell me. All right. Let's make a jump now. Now we're going to jump to this idea about, maybe it's not big of a jump. Okay, the definition of the limit of a sequence. Okay, the limit of a sequence. So let L be a real number. The limit of the sequence is L. And I could rewrite it or write that as the limit as n goes to infinity of A of n is equal to L. So as I plug in bigger n's, as the sequence goes on, what is it approaching? What is the sequence approaching? That's a big idea. This is not a series yet. It's about series in a second. That's when we'll jump. But the sequence, what are the sequence numbers approaching? And if the terms of the sequence approach a unique number, as L increases, then the limit of the sequence is said to converge to that number. So if the limit is 7, it means all your terms are approaching, they approach 7 over time, then the limit will be 7. If the limit of your sequence looks like it's approaching 0, then the limit is 0. If the limit to a sequence does not exist, then we say it diverges. So if the limit's infinity, or negative infinity maybe, or just kind of oscillates and doesn't behave very nicely, the limit of the sequence diverges. Okay, is this saying the same thing? Okay, so this is just saying, okay, let a function be defined to be, like, represent that sequence. So the explicit form of your sequence, that's going to be a function of n, and even though, like, in the function, you can plug in any numbers, including decimals, on the sequence, you can't plug in decimals, but we're going to treat them the same. It's saying if the limit of that function is L, then the limit of the sequence is L. So that lets us do quite a bit, and really we kind of just, I think, underappreciate what that just said. So if we say a function, this is how the sequence is behaving, like the function, then that sequence has the same limit as if I just found the limit of the function. All right, let's see if that makes any sense. All right, so the limit of a sequence. So for each of the following sequences, write out the first 4 terms. If you believe the sequence converges, make a conjecture about its limit. If the sequence appears to diverge, explain why. And assume each sequence has a beginning index of n and is defined forever, indefinitely. All right, so A of n. Let's list out some of the terms. A sub 1, Let me make this smaller. Okay, a sub 1 is going to be equal to, okay, plug in 1. Okay, this is going to be alternating. I see that negative 1 to the power of n, so it's going to go from positive to negative. In this case, it's going to be negative first, then plug in 1. Oh, we just did this, right? No, almost. 1 squared plus 1, 2. A sub 2 is equal to, plug in 2 for the exponent, 2 for n. So it'll be positive 1 over 2 squared. Why is it so hard? Okay, 5. That was embarrassing. Okay, plug in 3, so I have negative 1 times negative 1 times negative 1. So 3 factors that are negative, that'll be negative, over 3 squared plus 1 should be 10. A sub 4, I'm going to say it's a negative 1 to a positive, or an even exponent, so it'll be positive 1. 4 squared, so it'll be 17. So I'm thinking, even though they're alternating back and forth, back and forth, back and forth, it's like that second example earlier, right? Even though they're alternating back and forth, back and forth, back and forth, the limit, the numbers look like they are, where'd it go? Looks like they are approaching 0. I'm going to say this limit, as n goes to infinity, negative 1 over n to the n squared plus 1, I'm going to say that's 0. Because it looks like each term is getting smaller and smaller and smaller and smaller and smaller. I'm going to say it's 0, and therefore this sequence converges to 0. That's my L number. All right, let's do another one. All right, b of n, okay, so b of 1 is equal to cosine of 1 pi. So cosine of pi, and cosine of pi is negative 1, unit circle. b2 is equal to cosine of 2 pi. So unit circle, go around the whole time. Cosine will be 1. b sub 3, third term. Cosine of 3 pi, be 1. b4, cosine of 4 pi, back to, this one was negative, right? Cosine of 3 pi is negative. So this one looks like it's alternating negative, positive, negative, positive, negative, positive, but it goes from 1 to negative 1, 1 to negative 1. They're not both approaching the same number while they're alternating. So this one I'm going to say diverges. Since the limit as n goes to infinity of cosine n pi does not exist. The limit does not exist. It does not approach the same number. As I plug in more numbers, it just alternates. All right, just talking about sequences. This is fun. All right, c of 1 is equal to, plug in 1, so 4 times 4 over 1 plus 1 is 2. That'd be 2. C2 is equal to 4 times 8. 4 times 8 is 32 over 8 plus 1, 9. Okay, I'm going to plug this into the calculator, and that's about 3.556. C of, okay, what's this limit? Before we go any further, the limit as n goes to infinity looks like just 4 over 1, right? The limit in that form, the top, if I plug in infinity, it's infinity over another infinity, but the infinities on top are 4 times as big as the infinities on bottom, right? So L'Hopital's rule says the derivative of the top would be 12n squared over 3n squared. If I plug in infinity there, it's still going to be infinity over infinity, so I do 24n over 6n. L'Hopital's rule again, 24 over 6, which is 4. And that's terrible notation. It should say limit each time, right? The limit n goes to infinity at the top and limit n goes to infinity at the bottom. So it looks like 4, right? And you can just look at that and know it's just 4. And let's see if I keep plugging in these numbers. 4 times 27 is 108. On the bottom is 28. If I plug into my calculator, it's about 3.857. C4, plug in 4, so 4 cubed times 4 is 256 over 65, which is about 3.948. And it looks like the limit of those terms is approaching 0. No, 4. So it looks like it's approaching 4. So I'm going to say the limit of this approaches 4. So the sequence converges to 4. Okay, that's not, okay, no, just stop talking. Okay, converges to 4. All the terms later on in the sequence are going to get closer and closer and closer to 4. Oh, okay, this one. D sub n plus 1 is equal to negative 2 times dn. So to find, let's say n is 1. Then I'm plug in 1, that means d2 is equal to negative 2 times d1. If I wanted to find the third term, I take, so plug in 2, so plug in 2 would be d3 is negative 2 times d2. d4 is equal to negative 2 times d3. But here, d2 was equal to negative 2 times d1. d3 is equal to negative 2 times the one before that, which is negative 2 times d1. d sub 5 would be equal to negative 2 times d4, which is negative 2 times this. So if I wanted to kind of write this out, this would be negative 2 to the, what would that be? Something kind of like n plus 1. So the fifth term has 4 of those, so n minus 1 times the term before it, but something like this, right? Times whatever number, whatever d1 happens to be. So now I got to think, okay, is this alternating? It's alternating. As I plug in bigger numbers, I'd have this is 1 negative, 2 negatives, 3 negatives, 4 negatives. But notice this time they're not approaching 0. They're alternating, getting bigger, huge positive and huge negative. So that first example was alternating, but they're approaching 0. This one's alternating, but alternating between bigger and bigger negative and bigger positive. So this one, the limit does not exist. So I would say the sequence diverges. The word like diverge means it's not like getting to one point. Converging means it's getting closer and closer to the same number. Diverging, they're not approaching the same number. We are going to pause this video here. I'll make it 2 parts. So thanks for watching this video. In the next video, we'll talk about this idea behind a series. So thanks for watching. If you have any questions, ask me next time I see you in class. Bye.